In this lecture, we are going to see conditional expectation of a random variable. As we are familiar with the notion of expectation of a variable, with the help of its probability function, we shall now define conditional expectation of a random variable whose conditional probability function is known. The definition of conditional expectation are as follows. Let X comma y be a two-dimensional discrete random variable. The conditional expectation of x for a given y is equal to yi is defined by e of x by yi is equal to summation I xi into p of xi by yi, where this p of xi by yi is nothing but the conditional probability function of x. Next definition is for two-dimensional continuous random variable, that is e of x by yi is equal to integral over minus infinity to plus infinity x into g of x by y into dx, where this g of x by y is the conditional probability distributive function of capital X. Similarly, we can define the conditional expectation of y for a given x. We know that p of x by yi is equal to p of xi by yi divided by q of yi if q of yi is not equal to 0, and g of x by y is equal to f of x comma y divided by h of y if h of y is not equal to 0. Then we can also define the conditional expectation of x for a given y. Let x comma y be a two-dimensional discrete random variable. Then e of x by y is equal to summation I is equal to 1 to infinity xi into p of xi comma yi divided by q of yi. For two-dimensional continuous random variable, we have e of x by y is equal to integral over minus infinity to plus infinity x into f of x comma y divided by h of y into dx. It is important to note that from the definitions, e of x by y is a general function of y and hence it is a random variable. E of x by y is a value of the random variable e of x by y. However, for particular value of y, e of x by y is not a random variable. Based on these definitions, we have the following theorems. First theorem, e of x by y is equal to e of x, e of y by x is equal to e of y. For x and y are random variables. Proof: we are going to prove this for continuous case. The proof for discrete case can be got by replacing the integral by sum. That is, e of x by y is equal to minus integral minus infinity to plus infinity x into f of x comma y divided by h of y into dx is equal to mu of y. Say, where this f is the joint probability distributive function of x and y, and h is the marginal probability distributive function of y. Therefore, e of x by y is equal to integral minus infinity to plus infinity mu of y into h of y into dy. Substitute the value for mu of y, we get integral over minus infinity to plus infinity into integral minus infinity to plus infinity x into f of x comma y divided by h of y into dx into h of y into di. Taking the value of x out, we get integral over minus infinity to plus infinity x into integral minus infinity to plus infinity f of x comma y into dy into dx, assuming that the change of order of integration is permissible, which is equal to integral over minus infinity to plus infinity x into g of x into dx. Since integral over minus infinity to plus infinity f of x comma y into dy is equal to g of x. Therefore, we can say that e of x by y is equal to e of x. Similarly, we can do this for e of y by x is equal to e of y. Hence, the proof. Next theorem, if x and y are independent, E of x by y is equal to E of x, and E of y by x is equal to E of y. Proof. Already we know that E of x by y is equal to integral over minus infinity to plus infinity x into f of x comma y divided by h of y into dx. Substitute the value of f of x comma y is equal to g of x into h of y, since we know that x and y are independent, which is equal to integral minus infinity to plus infinity x into g of x into h of y divided by h of y into dx. Cancel this h of y will get integral over minus infinity to plus infinity x into g of x into dx is equal to E of x. Therefore, E of x by y is equal to E of x, and E of y by x is equal to E of y. Similarly, we can prove for E of y by x is equal to E of y. Next theorem, if x and y are independent random variables, E of x minus E of x by y is equal to 0. Proof. Since x and y are independent, we know that E of x by y is equal to E of x. Substitute this value over here, we get E of x minus E of x by y is equal to E of x minus E of x, which is nothing but E of x minus E of x, which is equal to 0. Thank you.